Thank you for joining us today in the third lecture of the third edition of the Current Topics in Heritage Science lecture series, which is organized within the E-RIHS Academy. My name is Tjasa Rievec, and I am a researcher at the Heritage Science Laboratory at the University of Ljubljana. I will be moderating today's lecture by Marc Walton, titled Computational Imaging for Cultural Heritage, Where We Are and What is Our Future. The recording of the lecture will be available on the E-RIHS YouTube channel. At the end of the lecture, you will also receive a survey to express your feedback. Please ask the questions in the Q&A function, and the questions will be answered by the speaker at the end of the lecture. If you experience any technical difficulties, do let us know through the chat. So our speaker today is Marc Walton, who is a professor in the Museum Studies program at the University of Hong Kong. Prior to this, he was the head of the conservation and research at Hong Kong's M+ Museum and worked in academia as a co-director of the Northwestern University Center for Scientific Studies in the Arts, where he was also a research professor of material science. He has led numerous scientific projects investigating art objects in collaboration with cultural heritage institutions, representing a broad range of disciplines and geographical reach. He has also held positions at the Getty Museum and the Los Angeles County Museum of Art after receiving training in art history, conservation, and archaeological science at NYU's Institute of Fine Arts and the University of Oxford. Professor Walton's most recent research is on developing and using imaging technologies in the field of conservation science to better understand how artworks were made and deteriorate. So Marc, thank you for being with us today to present this interesting topic.
Thank you very much for having me, Tjasa. The organizers of this online series, which I think is absolutely wonderful, is bringing together such a wide group of stakeholders. So I really appreciate all the organizing efforts that go into this. Let me launch my screen so everyone can see, and then that we can get started with this lecture. So everyone can see my desktop, I think, at this point, and the presentation, correct?
Yes, perfect.
Wonderful, thank you. What I'm going to be talking about is a topic I've been working on for about 10 years, but given the fact that I have 30 minutes to kind of condense down a lot of the work that I've been doing, I'm going to be skipping over a lot of the mountaintops on our way to understand what is computational imaging and why would we want to do it. In doing so, I'm going to give you some teasers along the way about the type of things that I would like to see the field steer toward. And particularly, I hope that there's going to be a lot of questions about artificial intelligence, the use of good curated data sets to be able to undertake the development of foundational models in this field, and what the benefits might be. I'm going to give you a little bit of a teaser about what we're doing in this area, but I think that it's a community-wide effort that we need to be focusing on. So let's, without ado, get started. I wanted to just say that there is absolutely, I'm standing on the shoulders of giants when it comes to analytical imaging in the field of cultural heritage. And we can go all the way back to the very beginnings of analysis in the field. In fact, back to the Fogg Art Museum at Harvard University, Alan Burroughs was given a position to look at X-radiographs for the very first time. And this absolutely changed not only the history of art and connoisseurship, it provided a path of looking at art that has really charted a course that we haven't looked back from, and is very much part of the way that we think about the field intimately. And of course, this has been carried on through time with such developments as infrared reflectography in 1968 with Van Asperen de Boer, and then even really more recently with John Delaney introducing spectral imaging to the field in around 2010, and Koen Janssens and Joris Dick developing macroscanning XRF in around 2013. These are things that are really very important because of the information carrying capacity. And I'm going to talk really throughout this entire presentation about what we mean about increasing the amount of information that we can capture in analytical images. In the case here, we can think about this from a point of view as a chemist. looking at individual spectra that are assigned to every single pixel in a two-dimensional array. That gives us a lot of statistical information to be able to mine that chemometrically. Or we can think about handing this over to an art historian or a curator in a non-technical way, and they can still see from a painterly point of view the technical aspects of painting. So it joins a lot of different stakeholders in the process to be able to actually see an image. So when we're thinking about information carrying capacity, I present what I'm calling the kind of traditional approach to imaging in the field, and that is to use some sort of modality of light, whether that be UV, IR, X-ray, visible light, and we illuminate an object, and we detect it on some sort of two-dimensional detector array. In the case of present day, we're talking about an array of pixels that have a particular width to them. In the past, we might have been talking about film when we're talking about something such as an X-radiograph. The end result, though, is an image which we can interpret in terms of the spatial dimensions of the original work of art, and that is something that can be looked at, interpreted by some sort of an analyst. By and large, when we think about the type of information that's encoded in these scenes, if we want to talk about the modalities of light being a certain way of encoding information into the scene, it has to do with how we interrogate depth within that painted structure. So for instance, we might be using infrared wavelengths to be able to penetrate very deeply into a painted structure, whereas if we're looking at just ultraviolet wavelengths, we're only looking at the top surface layers that we might be penetrating. With computational imaging, the approach is slightly different in the sense that we're thinking about using our illumination in a different way. We're encoding it to be able to unpack more information out of the scene. So I'm showing you here just a sample which we are some sort of way of changing the illumination frequency. We might be inducing a pattern. We might be changing the angle of illumination to be able to realize something that on a sensor might not be interpretable to the naked eye. So you need some sort of decoding on the other end to be able to produce an image. Why might we want to do this? Well, it's a way of being able to increase the information carrying capacity of the scene. We want to be able to pack more information into the measurement that we're making in a easier fashion. To be able to understand the amount of information that we can contain in a scene, I would like to show you this slide that I have borrowed very mercilessly from my colleague, Professor Florian Willemitzer, who is at the Wine College of Optical Sciences at the University of Arizona. And he posed what I thought was a very interesting question. What he said, okay, let's pretend that you're an optical scientist and you're working with some photographer, and that photographer can't figure out how to improve the blurriness of the images that he's creating with his digital imaging system. And Florian says, okay, well, I know my optics. I can figure out how to solve this problem. And so he lays out this problem that you see in front of you. You have some sort of object, you have some sort of imaging element, such as an objective lens, and you have a detector at the other end. And we're seeing that the image, the spot that is imaged from that object on that sensor has a rather large blur that's associated with it that goes beyond a single pixel and extends over numerous pixels, which causes some problems with the imaging. The way that he would think about this is through the space bandwidth product, the SBP, in which we have some sort of width of our sensor, and we have some sort of smallest resolvable element that I'm giving you by this change in X in some sort of direction, right? And that dividing one by the other gives you the numbers of degrees of freedom in your system. So the answer to his friend who's trying to figure out how to image something properly will be to say, well, you really want to reduce the blur that you're seeing on that sensor, so you probably need to change your objective lens to something that would be better matched with your array of pixels to be able to increase the number of degrees of freedom that you have in your system. For cultural heritage, I wanted to bring us back to about 20 years ago when these living photographs were first introduced to the field, and they so captured the imagination of numerous colleagues because you could see in a single image the three-dimensional qualities of an object, almost as if you were standing in front of it. You could see specular reflections, encaustics. You could see inside of an object almost by looking at how the transparency of different features. And this is all done by taking numerous photographs of an object and stacking them together and combining them together in some sort of fashion. The example I'm taking you from here was something that was presented at the Computer Graphics Forum in 2005 by Vin Muller. And is something that was readily adopted by the field and is known as reflective transformation imaging. And I'm giving you a sense of that here at one of the capture sequences. This is a project that we worked on with the E-RIHS Museum at the University of California. And we can see that we are changing the angle of illumination, as one can see on this mirror ball. And we're seeing this portrait, this Fayum portrait, which is coming from ancient Egypt, 2nd century AD, has all kinds of different ways of reflecting back to us according to what angle of light you're illuminating that scene with. If you think about this, you can take this entire stack of images where you have all these different angles of illumination and do a lot of different things with them computationally to be able to pull out different elements of the scene. To be able to increase the degrees of freedom in your scene, you want to capture all those angles of illumination. So what I'm showing you here is the stack of angularly encoded scenes of this Fayum portrait. We're using some sort of algorithm to decode it. In the case here, we're using something called photometric stereo. And from photometric stereo, we're able to separate out, say, things such as specular reflections and diffuse color. And you may ask, why do you want to see diffuse color and specular illuminations coming off of that object? Well, one of them, the specular albedo, I'm using the term albedo for color here, might be associated with features that are contaminating your scene that you don't want to have if you're trying to map the pigments that are in this portrait. You only wanted to have the diffuse component that's coming out of it. And of course, the diffuse color is what color carries the color information about our scene. And of course, we can also separate out the surface topography by using this simple way of decoding. Now, these are not things that can be done with a conventional imaging system. This is only something that you can actually do through some sort of optimization between your image capture process and the computation that you do at the other end to be able to realize your final result. A lot of this comes out of the field of appearance modeling and computer graphics. And why would the computer graphics community be interested in this type of subject? Well, for the very simple reason that if you go to Hollywood, and here's me in a studio in Hollywood that's run by Paul Debevec, they create these fantastically large domes of illumination to be able to animate actors in 3 dimensions in a digital form. And by capturing all these different angles of illumination, you can capture the very realistic looking features of the individual actors to be able to create films, anything that you might want to do in that kind of creative arena. What we're interested in doing here is trying to unpack the composition and structure of a work of art. And going back to this idea of increasing the degrees of freedom in our scene, we can do very controlled illumination sequences. We can measure the appearance of each one of those illumination sequences exactly. And we can assume some sort of bidirectional reflection function for our object. And what do I mean by bidirectional reflection distribution function, the BRDF? Well, this is a material property, and the Hollywood studios have spent a lot of time, effort, and money measuring everything from marble, which is very diffuse reflecting, to a metal object, which is very specular reflecting, and looking at how light reflects off of these surfaces by looking at every single possible illumination angle with every possible viewing angle to be able to create these functions that really capture the way that an object will look in reality once you've digitized it. The reason that we're using it here is that we can assume the way that paint is reflecting light from this object and extract out of it both shape and texture or color from our scenes. From my perspective, as someone who has worked very heavily in material science, you can also tie the BRDF back to its material properties. And I'm showing you here a diagram of what we would typically try to think about when we are talking about material properties from this point of view of light coming in and interacting with, say, a particle, what is called the scattering phase function. So you can imagine some sort of incident ray coming in, hitting a particle. Part of that light is going to be back scattered toward the viewer. Some of that is going to be forward scattered through other elements that are in some sort of painted structure. And we can imagine that this phase function is going to be a product of the wavelength of the incident light, whether the scatter is smaller in dimension than the wavelength of light or bigger than that wavelength, whether you have a particular refractive index of that particle, and what the surrounding medium is. All these come into play and shape and influence the magnitude of the BRDF function. So even going back down to that microscale influences the way that we're seeing at the macro scale. Putting this all together in something like a painted work of art, and looking at this cartoon of a cross-section in which we have all these different layers of painting that's on the surface, we can imagine this incoming beam of light, and it can be, say, specularly reflected from the surface, where the incoming beam of light is going to be reflected at the same angle as it leaving the scene. But really important for us, most of our imaging technologies, if we are going to be, say, doing photogrammetry or photometric stereo, it's relying on the fact that we have diffuse reflections that obey Lambert's cosine law, which means that the intensity of the reflected light is going to be proportional to the angle of the incoming light. But we also have further interactions that happen deeper within these painted structures. And in fact, we can think about the painted structure and its overall appearance once we see, say, a painting, the sum effect of lots of multi-bounces and scattering and absorption processes that are taking place much deeper within these painted layers, which means that the cross-section of the light that is actually being transported through those painting layers is that's much deeper than we might consider just a single point on the painting. And this plays a significant role in how we unpack how light interactions with matter actually takes place. The work that I have done throughout the last 10 years has focused on both looking at the macro scale and micro scale. From the macro scale point of view, my group has done a lot of work on metrology and morphology. I'm showing you an example in this particular slide of using some sort of structured illumination, using an iPad, and we're very interested in using consumer devices, off-the-shelf consumer devices, to be able to do computational approaches to realize surface shape of objects, because they're cheap and readily accessible, and you can tune them to get really very incredible results. So that's one side of it. The other is to be able to think about combining together different modalities of light. So for instance, I'm showing you here in the lower left-hand corner, if you were to combine together, say, an X-ray fluorescence cube with a reflectance image cube, you can exploit the different amounts of penetration that they would have into a painted surface energetically to be able to do source separation. So you can look at hidden layers of hidden features by finding some way of algorithmically combining them together. The organizers of this current presentation, however, asked me to talk about some of the work that I've been doing at the microscale. And so I'm going to be talking about two projects that we've been working on. One of them is reflective optical sectioning microscopy, which it goes back about 5 years when we first developed this type of microscope. And then second of all, I wanted to talk about a new project that we've been working on, which is transmissive single-shot polarization light microscopy. Using very similar concepts to what I've already introduced, which is a dome of illumination to be able to increase the angular diversity of your measurements, to increase the numerical aperture of your illumination, to be able to realize different results. So the work that we did in this goes back to, say, 2020, and this is one of the papers that we published on using oblique illumination to be able to do spectral imaging. And you might think, well, why would you have to do something computational to be able to do spectral imaging? You put a spectrometer on top of a microscope, you scan your sample, you should be able to get something. Well, it's not so simple. And I recall this diagram that I showed earlier, that we have all these subsurface scattering events that have very long range cross sections. Because of that, that individual particle that we want to get a reflectance curve from down at the micron scale might be the sum component of a lot of different scattering events that are happening outside of that particle. So getting a clean reflectance curve becomes very difficult. So we thought about different ways of being able to solve this problem. And what we came up with is the configuration that you see here on the left-hand side, in which we have an illumination arm that's separated from our detection arm. In which we're able to move that illumination arm to be able to create a dome light illumination structure. This is what it looks like here. where we have this illumination and detection arm decoupled. We're able to move that illumination arm in between 35 and 90 degrees to get some sort of polar rotation. And we're able to rotate the sample around to be able to get azimuthal rotation at the same time. And we pack all this in under a long working distance objective that's around 20x. And to illustrate what this does is that you can imagine starting off at some low angle of illumination, increasing that to a high angle of illumination, and then spinning it around in 3 dimensions to be able to realize this large angle of illumination, taking each one of these different illumination angles as a separate photograph. And this is the same thing as capturing a larger scene using a dome of lights, like I presented before with the photometric stereo technique. This is just to give you an intuitive understanding of how all this equipment works in this microscope, very mechanical, and being able to move the device in different ways to be able to realize the measurement that you're trying to make. Once we've captured all these angles of illumination, I'm not going to be talking about calculating surface shape very much, which you can do with this technique, but I want you to focus on this diagram E that I have, which is a cross-section of the way that 2 angles of light might come together in sum to be able to produce a much smaller interaction volume that we can combine together analytically to be able to only look at a very small sliver of that larger lobe of the way that light comes in and scatters through that sample. From a much more intuitive point of view, if we can take a look at the average of this cross-section, if you take all the angles of illumination, you sum them together or average them together, it produces what you would typically find in a typical dark field or bright field illumination of a cross-section. And you can see that in this inset, that there's a lot of blur that's associated with that technique by combining all those lighting angles together. However, if you take the minimum projection through all those different angles, you are eliminating a lot of that scattering, only looking at that small little subsection of our interaction volume. And we can see that the particles are much better refined in that 1 micron zoomed in image of that area, which means that we're able to achieve a higher resolution simply by using all these individual illumination spots on our object and combining them together in a computational way. And of course, the reason that we want to do this type of work is to be able to make these measurements, each one of these angular measurements, at a variety of different wavelengths, starting at 400 nanometers and then collecting every 5 nanometers and 5 nanometer spacing across the visible spectrum. So going from 400 to 1,000 nanometers, which creates a hyperspectral cube, which we can then factorize and determine the end members. So we can map pigment phases across a cross-section. And here I'm showing you one cross-section that we analyzed where we're able to take a look at the distribution, say, vermilion, carmine, ultramarine, lead white, and Prussian blue, all from a single cross-section. Why would we want to do something like this? Well, instead of having to take it to a very expensive piece of instrumentation like a scanning electron microscope, we can do a lot of this phase mapping within something simple like an optical microscope, which reduces the cost and the barrier of entry of being able to do the type of mapping. For the remainder of this presentation, I wanted to concentrate on a current project that we're working on, which again exploits the same sort of idea of using a dome of illumination, such as I'm showing you here in this cartoon of this microscope, in which each one of these LEDs that form this dome of illumination can be separately used to be able to shine an angle of a light through our microspecimen. And here we're creating polarized light microscopy images where we're distributing pigment particles or other sorts of particles within some sort of binding medium. Like Cargyle melt mount. Here I'm showing a quartz particle that's mounted in Cargyle melt mount, and then detecting it on a camera in which every single pixel has some sort of lithographically deposited polarization filter, such that with a single snapshot, you're getting 0, 90, 45, and 135 degrees rotation of the polarization filter as opposed to your analyzer. And I should mention that in this microscope, it's a typical PLM type microscope where the light is going through a polarizer and then our analyzer is embedded on our camera. Of course, we can combine all these angles together, and I'll show you this animation of what this looks like. Combine all these angles of illumination together, and each one of these images in these sequences of these videos is showing a different capture. combine them together to be able to create phase information using techniques such as Fourier topography. But even looking at this raw data that I'm presenting to you here, we can already start to see the three-dimensional quality of these particles, which could be very useful for diagnosing different features about what's going on, whether they're deteriorating or deliberately manufactured as something that we can pull out of it. What I want you to pay attention to, though, is the interference colors that we're seeing on this, which is the result of the polarized light interactions with that particle and the filters that we're using. If we're to think about polarized light microscopy, and this is, by the way, is going at a very rapid clip when it comes to this. There's a lot of details and subtleties that are worth discussing. But we would be faced with an image that looks like the one on the left, where we have this elongated particle, we have a black background, and we know that our polarization filters are crossed in this particular case, and we can exploit this information. So by knowing the thickness of that particle, which is 17 micrometers, and we can measure that off from the calibration of our image, we could find the birefringence of that sample. And what I mean by birefringence is that if you have an anisotropic material, light is propagating through it, there's going to be more than one refractive index pathway, and that the phase difference between those different refractive index pathways will result in an interference color once they combine together back on your sensor. So what we're seeing here in this Michel-Levy chart, which is the type of chart that microscopists will use to be able to understand what the birefringence is, we can take a look at the color of that fiber, and we can match it up with the Michel-Levy chart, and we can say, oh, okay, we draw a radial line that's going from the origin out to this axis up here, and we can see that we have a refractive index of around 0.025. That's wonderful. We're very happy with that situation, and how polarized light microscopy has been used for almost 100 years now. But going the other way, you all of a sudden realize that you can use the measurement by refringence. If you know that you have some sort of measurement by refringence, we can also find 3D shape from that. And so we started thinking about this problem going the opposite direction and saying, well, we could exploit this polarized light microscopy technique to be able to extract 3D shape. So just a quick note about the Michel-Levy table is that you might think about a particle that is 45 microns thick. You have a refractive index, you have a birefringence of 0.019, and that if we draw a line across this this 0.019 contour line, that we can produce that yellow color, which would be the type of interference color that we want to see. Another way of showing you birefringence and thickness relationship more directly is the Wraith-Sorensen chart that I'm showing you here. And again, we put this birefringence value, and we can see that at 45 micron thickness for a particular specimen, it produces a yellow color. But we have all these different options, so it's a non-redundant answer here to be able to look at this. And so, for instance, we could also achieve that same sort of color yellow if we were on the 0.034 contour line, and we had a thickness of, say, 25 micrometers. And that's kind of one of the ambiguities that I wanted to point out. We have this quartz particle here. You can see all these different interference colors. And if we're to do an analysis of this particular quartz particle, we might assume that we're looking at something that has a birefringence of 0.034. In fact, it's not like that at all. The birefringence of quartz is 0.009, which means that we're way out of the scale of this Michel-Levy chart, and this quartz particle is actually several millimeters thick. So when we're thinking about this problem, this forward simulator that where we're actually making these measurements, we can think about this in terms of having some sort of energetic field propagation that is going through a polarizer. We have some sort of phase difference that's occurring within our specimen, and then we have our imaging and our analyzer angles that are all built into this. And we can use a very simplified equation to be able to map all this up. So our forward model for actually looking at how light interacts with the particle really boils down to this very simple equation that I'm showing you here. The trick here is that we have to calibrate our spectroscopic system with RGB space, meaning that we have to make sure that a Michel-Levy table that we're synthetically creating digitally matches up with the reality of our measurement. So I'm just pointing out here that we have to make this conversion and actually do some calibration steps between that we don't have time to talk about in this presentation. The other thing that we have to do is we have to calibrate for our polarizer and analyzer direction. And this is done very simply. We can take a background measurement. We can see what these RGB values are for the background measurement once we've calibrated our system. And we can figure out what the intensity of that background is and find out where on this chart between 0 and 1, which are 1 being completely open, 0 being the polar and analyzer being completely crossed, where we are within that sequence. And we can get very precise measurements of where we are in that sequence of adjustment of the polarizer and analyzer of this. And this is very important to be able to get good quantitative results. So when we combine all this together, we create some sort of objective function like I'm showing you here on the left-hand side, where we have our forward model and we're taking the capture information that we have that we can measure precisely, and we're optimizing between these two things. Such that we can produce a reconstructive image such you see here on the right and actually predict our three-dimensional map, and with a very small absolute error. And you might be wondering, well, so what? Why would you want to do this type of work with polarized light microscopy? Because I've been very happy up until this point using it in the traditional way. Well, we would really like to introduce artificial intelligence. And the real reason for us doing this project was not so much to be able to back out 3D shape from the Michel-Levy table, but we wanted to create all kinds of arbitrary digital images of theoretical particles based on refractive indexes, based upon known birefringences, where we can control all the parameters and shape of our image, but using a principled approach such as this forward model that I'm presenting here. And the reason behind this is the other part of this project where we're trying to use AI to be able to retrieve these microscopic images in a real way. So we're doing it in two fashions. One is we're creating these synthetic data sets that I just described to you, but we're also scraping the web for all the PLM and microscopic images associated with culture heritage projects that we could lay our hands on. So far, we have 4,000 of these that we've taken from websites and books. And we're feeding them into foundational models such as those developed by OpenAI and their CLIP model, where you're finding some sort of embedding between text and image, and then using a retrieval pipeline to be able to then, say, introduce an image into this framework to be able to get some sort of text or label that you would want to have for that image, or vice versa, introduce some sort of text parameters and show all the different possibilities for that description that you're writing into a query. So basically making what I would call a ChatGPT or DeepSeek, because I'm in China right now, I should mention that, for polarized light microscopy images. And our preliminary results in this are considerably good, actually, surprisingly good for doing just a minimal amount of work to be able to bring all this data together. So what I'm showing you here just is really very much a teaser, and then I will stop talking, where we're using UMAP, which is clustering the vector output of our CLIP algorithm to be able to produce these different groupings of information. So we can clearly see that things such as all pigments are grouping together, paper and textile photomicrographs are grouping together, all the polarized light microscopy images of natural fibers are grouping together, and things such as wood cross-sections are all coming together. I would have gone into the details of other aspects of this plot, which is very interesting because you could see separation, different modalities of light, and really clear separation of different types of particles at the micro level. I'll end with this. The idea, why would we want to do this? Why would we want to do this clustering? Is because when we first started this project, and when you're training an AI model, you don't know what sort of class, in this particular case, we didn't know what sort of classes they were. And it comes back to the curation of good data sets. We didn't have any real good data sets to be able to train a model when we came to polarized light microscopy, and we realized we had to create them ourselves. So this is a way of cleaning up the data that already exists in the community to be able to create a better labeled data set, a better trained data set to be able to do the projects that we would like to do of AI in the future. So we'll leave it there, and I will open up the floor for questions. So thank you very much. And I also wanted just to thank my collaborators in the project. Manuel Ballester did a lot of the forward modeling for the polarized light microscopy model. Asami Odate is my postdoc that's working on the AI. And Agalos Katsagalos at Northwestern University has been one of my prime collaborators over the last several years. So thank you, and I look forward to your questions.
Thank you also from my side for this amazing lecture. Let's give the audience a minute to type in their questions. So please, everyone is welcome to ask whatever has come up to mind during this. And I'd like to take this minute to also announce the next lecture in our series, which will be happening on the 24th of April and delivered by Laura Brambilla. It will be called Acoustic Emissions Techniques Applied to Heritage Historic Vehicle Engines Restoration.